Hello, I'm an alien. You can call me Al. This is part 6 of my message. It's about environmental bonus points. Now, the inhabited zone of the Earth is like the skin of an apple, thin and fragile. The heat content of the whole atmosphere is only equivalent to 3 meters of ocean. And it's this skin which is heating up at the moment. The sea, which is on average nearly 4 kilometers deep, is an enormous heat sink, and you can use this to buy time. By mixing the heat more evenly, you can keep the surface zone cooler. Of course, this is not a long-term solution, but untended, the heat will get to the deep ocean anyway, within a few thousand years. As a bonus, the thermal expansion of a mixed ocean is only half of that of a heavily stratified ocean. That means that the expansion of the surface waters, when they get very hot, is far in excess of the cooling. So you would halve, effectively, the effective ocean level rise. Now, the great ocean conveyors, for example the Gulf Stream, move huge amounts of heat from tropical up towards the polar zones and back again. But they need to shed almost all of their heat before they get dense enough to sink. Now, the result is that as tropical waters get warmer, that means that more and more heat is being dumped into the polar regions before this cycle can take effect. This melts the ice cover and reduces the reflectivity of the Earth. It also risks destabilizing polar methane hydrate. This was the villain that we talked about last week. By pumping hot water down, or cold water up, in tropical zones, you still get your ocean mixing, but you bypass the poles and reduce the negative effects. Here's an illustration of a machine for pumping hot water down. The hot water column, as it is called, is perhaps the simplest scheme for stimulating ocean circulation. This time by sending a stream of hot, salty water into the ocean depths. A floating concrete unit, several kilometers long, combines a beach, a catchment pond, and a downpipe. Mid-ocean wave energy is used to fill the pond, which is some meters elevated above ocean level, by inducing the waves to run up a smooth inclined plane called the beach and transfer their kinetic energy into static head. From the pond, a vertical pipe allows the water to flow by gravity to the ocean depths, where it is diffused into the current over a wide area to prevent formation of a return chimney. A head of 2 meters is sufficient to circulate large volumes of hot water. In addition to transferring heat, the water also moves dissolved air to the depths, helping to prevent oxygen starvation, which is predicted as one of the nasty side effects of global warming. Here are the numbers. A 5-kilometer machine redistributes 160 cubic kilometers of water per year, equivalent to 500 gigawatts continuous of heat, which is like 250 power stations. 800 such machines could completely redistribute our current global warming excess. However, by modifying this design slightly, you can greatly improve the outcome. By adding a series of wheels and a riser pipe, the descending stream of hot water drives a series of pistons connected to an endless rope. And as the pistons return to the surface, they bring up a column of very cold water via a riser pipe. This deep cold water, say 2 degrees, is diffused some 10 meters below the surface. In other words, the machine not only puts hot water down, it brings cold water up. At full capacity, the machine is shifting more than 1.2 terawatts of heat, equivalent to the output of 600 central power stations. Although rather more complicated than the hot water column, this machine has several advantages. For the same amount of wave energy, it circulates 30% more heat because of density differences. The cold water plume at the surface has significant beneficial effects on the weather, for example, moderating hurricanes. Up with the cold water come nutrients, which stimulate plankton absorbing vast quantities of CO2. Fish thrive. If you couple that with marine park status, you will have an oasis for fish and coral revival. It should be appreciated that although the great ocean currents, like the North Atlantic conveyor, move vastly more water, the temperature difference is very small, since the surface water has to cool to nearly 0 degrees before it's dense enough to sink. So as a result, these machines, which move very hot water down, can produce an equivalent cooling effect. Here are the numbers. The volume of the oceans, 1,220 million cubic kilometers. The heat capacity of seawater, 1.18 kilowatt hours per cubic meter per degree centigrade. The annual heat overload, 3.5 million terawatt hours human input. Result, the annual temperature rise, 0.0025 degrees centigrade, i.e. 1/4 degree per century. Now, you might ask, why is this figure so much less than what we're experiencing at the moment? Well, the answer is because that's if you spread the heat over the whole ocean. At the moment, it's only the surface layers which are getting warmed up. Here's a last thought. The Gulf Stream carries 700 trillion kilowatt hours of heat up to the Arctic before it's cool enough to sink. Much of this heat helps to melt the ice caps. By pumping hot water just 3 kilometers down, you shortcut this 16,000 kilometer circuit, avoiding overheating of sensitive polar areas with the consequent nasty secondary effects.